Hello and welcome to the lecture on adversarial examples, where we will get to know about adversarial robustness, training, examples, and ways to generate them. Adversarial robustness describes the ability of a trained neural network or any machine learning model not to fail on the perturbed input images or inputs that are given during the test time. Such perturbations are generated in a special way to ensure the failure, and adversarial machine learning is concerned with describing techniques for such generation. In order to protect the model, we can add adversarial examples to the training set and thus ensure that the model will know how they look like and the robustness will be improved. This is called adversarial training. Let's talk about adversarial examples now. An adversarial example is an input to the model that is specifically designed to fool it, meaning to cause an error in the prediction. Even when the test error of a model is very low, it can fail to predict correctly if the input is modified, especially if it is modified for fooling the model. With it, the modifications can be imperceptible by a human. This means that the models are not learning the task the way a human will. Adversarial examples are not unique to deep neural networks. They can be generated for different classes of machine learning models. They pose a serious security issue when machine learning is used in practice. Think, for example, of an autonomous driving and making a car believe that it is not a stop sign but a speed limit sign, or a way to prevent face recognition from surveillance videos, or even worse, make a model believe that it's another person. Here you can see an example of adversarial perturbation that leads to misclassification with high certainty. So initially the network was predicting correctly that it's a golden retriever, rather confidently, and after adding this small perturbation, it's actually zoomed in order for us to be able to see what is happening there. It predicts that it is plain with 99% confidence. These adversarial examples are not anymore imperceptible by a human. You can see these glasses added to the photos, but they lead to a change in a prediction. They are predicting celebrities in the second row, or rather the model is predicting celebrities in the second row, so only glasses are added, and of course it shouldn't change anything. This type of adversarial example shows that a seemingly random noise can be generated in a way to make a model recognize a particular class in it with high certainty. So obviously, for a human, this noise doesn't make any sense. Nevertheless, the network will be sure that this is exactly what is drawn there. Adversarial examples can be generated not only in image classification tasks, but also in audio recognition. Here you can see how a small perturbation in an audio wave leads to the complete change of the recognized text. So initially it was the best of times, it was the worst of times, adding the small noise, and the network recognizes it is a truth universally acknowledged that is single. So it doesn't make any sense. In the following, we will see how an adversarial example can be generated. We consider a generation of the head X that is very similar to the original X, where X is an input, but it fools the target model. Training a neural network means to minimize the loss on the inputs with respect to the parameters theta. Quite opposite, for finding an adversarial example, we need to maximize the loss with respect to the input, having the parameters theta fixed. In more details, we optimize the perturbation data to maximize loss and limiting the values of delta itself to some area big data. Usually the possible perturbations are in the epsilon size ball with L infinity metric, meaning that it limits the maximal change among all the dimensions. So as you can see in this formula, we are basically saying that each element of our delta should be less than epsilon here. We also can decide on the possible perturbations depending on the input x we are using as the original input. Let's again refresh our understanding. We have some original input x. We have perturbation delta. We're adding perturbation delta to the x, and we are getting the x hat, that is our adversarial example, and leads to the mistake in the prediction. While we can simply maximize loss, thus obtaining an adversarial example that forces a model to predict wrong, we can also create a targeted adversarial example. Such example forces a model to predict a particular selected class. For this, we must both maximize the loss with respect to the correct answer and minimize for the desired answer, for the desired label target. Adversarial training. Adversarial training is a protection technique that allows to make models more robust to adversarial attacks, meaning showing them adversarial examples and leading them to fail in the prediction. For this, we minimize loss on the adversarially perturbed training samples such that we minimize the maximally possible loss when inputs are perturbed. You can see in this formula that it's simple minimization with respect to the parameters, but not on the original examples x, but on the perturbed plus delta, where delta is chosen such that loss is maximized. And this is exactly the formulation of the adversarial training. If we are training with mini-batch SGZ, we essentially must first modify each input in order to maximize the loss. That's the first step. And then update the parameters in order to minimize the obtained loss values. That is the second step. Keep in mind that such simplification is valid when we assume convexity of our optimization problem. And that is exactly claimed in Tanskin's theorem. And later on, we will see what can be done when the problem is non-convex. Talking about convex models, we can consider linear models. In case of the linear model, the adversarial training optimization can be written in a closed form. Let's consider a logistic regression for a binary classification task. The hypothesis space consists of the functions of such form, you can see it here, where theta is our logistic sigmoid function. When we put the labels to be +1 and -1, the logistic loss will have the following form that we can rewrite with a function notation depending on this argument. Thus, the maximization of the loss with respect to the input for such model looks as following. First, let's notice that the loss function, the big psi, is monotonically decreasing. So basically it looks like this on the plot. For monotonically decreasing function, maximization of the value means minimization of the argument. Therefore, we can rewrite the maximization problem as minimization under the function. And then we see that only part of our argument depends on delta, and thus we are moving out everything that doesn't depend on delta, and we are left with minimizing only this part. Let's first assume that our label is +1 and restrict adversarial perturbations to an epsilon ball, like we were discussing earlier. It means that each element of the perturbation vector lies in between minus epsilon and plus epsilon. Since we assume that y is plus 1, the overall argument, once again, remember this one, will be minimized with each element of delta being minus epsilon if the corresponding weight is positive and plus epsilon if it is negative. Correspondingly, if our label is minus 1, then the solution flips. And this allows us to write down a closed form for solution for the minimization problem that doesn't actually explicitly depend on x, if you look at it. Substituting the found solution and simplifying the formula, we obtain the arguments that will be put to the original loss in order to get its maximum. So first we are putting our delta star into the minimization problem, getting this. Then we are putting it to the loss function, getting this. And finally, we can find the form of the loss that must be minimized in order to perform adversarial training for the logistic regression. And it will look like this. Let's consider an example with a MNIST dataset that is reduced to two classes, ones and zeros. We can easily train a logistic classifier to a very low misclassification rate on the test set. Next, we generate adversarial examples with perturbations from an epsilon ball with epsilon equal 0, 2. We can do it so. We can select epsilon any way we want. Using the closed form solution for the perturbation maximizing clause that we just arrived, we can easily build such adversarial examples. Since optimal perturbation delta star doesn't depend on input x, it will be only one perturbation pattern that we see here on the image for all the inputs. For the opposite label, the black and white pixels will flip. We can vaguely recognize one in the black pixels on the image here. Correspondingly, when the pixels are flipped, round forms will recollect 0. Here you can see the perturbed input images. On each, this pattern is there in the corresponding form depending on the label of the original image. And of course, it's not as dark as we saw before because it's less than 1 in the intensity. The misclassification error on such images grows from nearly 0 to 80%. When such perturbed images are simply added to the training set, thus allowing for simplest form of adversarial training, the misclassification error again becomes less, as you can see here. Now let's move to neural networks. And as we know, neural networks training is a non-convex optimization task. So we cannot already use the Dunskin's theorem, and we have to approximate the optimization task for maximizing the loss with respect to input. One of the most popular methods is called projected gradient descent, or PGD. And you have to keep in mind that formally, of course, we're performing ascent since we are maximizing loss, but the name is still projected gradient descent. Each step of basic PGD algorithm updates the adversarial perturbation by using the corresponding loss gradient and then projecting the result onto the fixed perturbation ball. You can see the formula here. This big P is projection. We again consider an epsilon ball, then the projection is simply clipping the perturbation value into the interval between minus epsilon and plus epsilon. Here. This allows us to rewrite the optimization step of PGD using the clipping function instead of projection. So it's the same optimization of the perturbation, and we're clipping it to the needed range. On these images, you can see how PGZ works. After the gradient step is made, the result is projected back into the area of interest. So here's our epsilon ball in L2 norm, and we are returning back to it. Here we are making more steps, and the norm here is already L infinity. And you can see that only on the last step we are going out from our epsilon area, and we are returning back. Finally, we will discuss another adversarial perturbation generation method that is named fast gradient sign method, or FGSM. It can be considered as a simplification of PGZ via fixing the perturbation space to the epsilon ball and forcing the perturbation to be always either plus epsilon or minus epsilon, depending on the sign of the gradient. This can be, for example, achieved by selecting infinitely large learning rate alpha, exactly how we say here. Another simplification of FGSM that we perform only one optimization step, not multiple steps like in PGZ. Finally, since on the initial step perturbation is equal to 0, we are simply taking gradient with respect to x. Like this, we are obtaining the formula for the perturbation according to FGSM, that is epsilon multiplied by sign of the gradient with respect to our input. Here you can see how FGSM forces the perturbation to stay inside of the allowed epsilon space, with it slightly changing the direction of the step. So initially we were directed here, and once we are projected back, we kind of directing here. This approach can be considered as the simplest way to force updates to stay inside of the epsilon ball, because we are mainly saying that our perturbation can be only minus epsilon or plus epsilon. Note that the optimal attack we derived for the linear classifier corresponds to FGSM perturbation. Here you can see how adding an extremely small perturbation that corresponds to the directions of the gradient, like in FGSM exactly, we can fool the network in order to make a false prediction with high certainty. We are moving from Panda to Gibbon with 99% confidence. That's all. Thank you for your attention.